Then I would now like to introduce our second speaker, Professor John Barrow. I first met John last Sunday evening at a dinner with Sydney and Balazs. Prior to that dinner, all I knew about John was that he is a cosmologist, a theoretical physicist, and a mathematician, and that he was highly recommended as a speaker for this series by Martin Rees. So I went on the internet and looked him up. And some of what I found is written in his bio that we distributed by email before. But I also found a number of quotes of him, by him. Some are from his books. He wrote 22 of them. Some are from the speeches he gave when he received the Templeton Prize in 2005. The Templeton Prize, I should say, honors a living person who has made an exceptional contribution to affirming life's spiritual dimension, whether through insight, discovery, or practical works. And here is some of the things that John said. Many of the deepest and most engaging questions that we grapple with about the nature of the universe have their origins in a pure religious quest for meaning. The concept of a lawful universe with order that can be understood and relied upon emerged largely out of religious beliefs about the nature of God. And if a religion is defined by a system of ideas that contains unprovable statements, then Gödel taught us that mathematics is not only a religion, but it's also the only religion that can prove itself to be one. And another one. While we have no reason to expect that our position in the universe is special in every way, we would be equally misled were we to assume that it could not be special in any way. And the universe has imposed aspects of its structure upon us by the inevitability of the forces of nature. In a world where adapters succeed, but non-adapters fail, one expects to find vestigial remnants. Many of these adaptations give rise to a suite of curious byproducts, some of which have played a role in determining our aesthetic sense. We are products of the past world, where sensitivities to certain things were a matter of life and death. History is full of people who thought they were right, absolutely right, completely right, without a shadow of a doubt. And because history never seems like history when you are living through it, it is tempting for us to think the same. And finally, there are only certain intervals of time when life of any sort is possible in an expanding universe, and we can practice astronomy only during that habitable time interval in cosmic history. Fortunately, we live in such a time, and fortunately, we have John Barrow here to tell us about it. Please give a warm welcome to John.
Well, thank you very much. It was great to listen to Sydney's brilliant exposition of what I would call inner space. And now you're going to hear something about outer space. Cosmologists rather modestly describe themselves usually as specialists, but specialists in the whole universe and everything that surrounds it. So I'm going to attempt to show you something about modern thinking about how the universe got into the state that it's presently in, and what that state has got to do with the complicated and biological processes that interest us in this lecture series. In my title, the word evolution is being used here, but in a less rich and complicated way than it will be by biologists like Sydney. For astronomers, evolution is just a byword for change, for development. It doesn't carry with it any of the other ingredients of evolution by natural selection. If you wanted to do that, you would have to develop a slightly more exotic type of cosmological theory aimed at explaining rather peculiar aspects of the universe. Some people do that, but that's not my task today. Another point of connection between our themes of inner space and outer space is that I think between them they are based around the two greatest scientific discoveries of the 20th century. The first, the DNA double helix of biology, but in cosmology, the discovery of the expansion of the universe. So before the late 1920s, the general picture held by philosophers, astronomers, and scientists over thousands of years was that the universe of space around us was rather like this fixed stage here on the floor. It was something that was absolutely unchanging, a reference system to which you could refer the motions of planets and comets and other heavenly bodies. But it was unchangeable by anything that could happen in the universe. What Newton called absolute space. But Einstein changed all that. He showed that space and also time were dynamic entities whose structure and rate of change and flow were shaped by the material contents of the universe. That space was not a fixed stage like this floor here, but it was rather like a rubber sheet or a trampoline. And it was shaped by the movement of mass and energy upon it. And what Einstein also did for the first time was to turn the study of the universe, or cosmology, into a science. Because Einstein's theory of general relativity provided for the first time a set of mathematical equations, partial differential equations, all of whose solutions, and there are an infinite number of them, describe entire universes. Fortunately for us, our universe is very well approximated by particular solutions of Einstein's equations, which have very high symmetry and relatively simple behavior. So for the first time, you could find mathematical solutions which would enable you to make astronomical predictions, and you could test whether those solutions were accurate. Before Einstein, I like to think of cosmology as being a branch of art history. You could paint any picture you like about the universe. It could be cubical. It could have a succession of turtles placed one on top of the other. It could be a giant cosmic pyramid. There's no one to prove otherwise. There's no theory which generates descriptions of entire universes until Einstein comes along. Well, Einstein's theory predicted the existence of universal solutions which were not static and unchanging, but which changed in time. And at the end of the 1920s, discovery was made by Hubble, Lemaitre, and Amundsen and others that the universe is indeed in a state of overall change, a state of expansion. And here's a picture which summarizes the present state of play with data. This is not all the data, it's just representative of different types of data. So what is being shown here is the speed of recession of sources of light in the universe, plotted against distance away from us, inferred by apparent brightness or something similar. Hubble's original observations would fit in a tiny dot down here. But people work so hard in this subject at seeing things which are fainter and further away, thanks to the efforts of quantum electronics and the physicists who work in this area, CCD detectors and so on, we can now see to fantastic distances, millions of parsecs, 400 million parsecs. A parsec is a few light years. And you see the overall trend here, that the speed of recession increases roughly linearly with distance. Something interesting happens when you get to very great distances, which led to the award of the Nobel Prize for Physics in 1999, for work done in 1999, rather. And I'll talk about that at the end of the talk. Well, let's unpick this idea of the expansion of the universe. It sounds very simple, okay, the idea of expansion. But once you start to think about it, it's not so straightforward. I mean, what's expanding? Are you expanding? No, not because of this. Is the Earth expanding? No. Is the solar system expanding? No. Is our galaxy expanding? No. Are the local group of galaxies expanding? No. Why? Well, because all those structures are held together by other forces. In the case of you and me, chemical forces. In the case of the Earth, stronger local gravitational forces that overwhelm the effect of the global expansion over their dimension. To find the traces of cosmic expansion, you have to go out to the scale of great clusters of hundreds and thousands of galaxies. And these are the markers of the cosmic expansion. They are like raisins in a great lump of dough that's placed in the oven. The raisins don't expand, but the dough between the raisins does, and they are pushed apart. So that's what's expanding. But the next odd question you ask yourself is, well, if everything's expanding away from us, doesn't that mean we're at the center of the universe? And Sydney has just told us we can't think of ourselves as being at the center of the universe. And Copernicus tried to persuade us that we shouldn't think in this way either. But the expansion of the universe is not an explosion. It is not exploding into anything. There is no center to it, and there is no edge. So, again, the words sound straightforward, but they don't add up necessarily to mean anything. So we need to look at a couple of examples. Let's suppose first that we're dealing with an infinite universe, and Mr. Escher from Holland comes to our help in visualization. Suppose we have an infinite universe, like this array of girders that goes on forever. There's obviously no edge because it goes on forever. It's not expanding into anything because there is no anything for it to expand into. Now, if you stand at any point in this universe, any of these crossover points here, and look around you, you will think you are at the center of the universe because every point behaves as though it is the center. If we raise the temperature in this picture, then all these girders would expand. And if you stood here, or here, or here, you would see everything expanding away from you as though you were at the center. So in an infinite universe, every point acts as though it's a center. This was why it was such a dangerous idea to Catholic theologians and philosophers in 1600 when Bruno was burnt at the stake for proposing this idea of the infinite universe. It seems harmless, but in an infinite universe there is no center. There can't be a special place where the Earth is located, a privileged position. So this is why this might be a philosophically dangerous idea. Well, it's all very well thinking about infinite universes, but how could this be true for a finite universe? Suppose you have a finite universe which is two-dimensional like this piece of paper. How could there not be a center and not be an edge? Seems impossible. But Einstein's theory, you remember I mentioned to you, introduced this idea that space is curved by the contents of the universe. And if there is sufficient material within it, the space can be curved so that it is not flat like that sheet of paper, but instead it's curved like the surface of a ball. So the surface of this ball is finite. You only need a finite amount of paint to paint it, but it has no boundary. If you are an insect and you walk around it indefinitely, you will never run into an edge. So curved spaces are unlike flat spaces. They can be finite without an edge. And the expansion of this little two-dimensional curved universe is like inflating this balloon. It gets larger and larger. If you locate yourself at one point, you see all these other little galaxies expanding away from you as though you were at the center. And the same is true whichever point you locate yourself at. The real center of the expansion in this little analogy is not on the surface of the balloon. So I hope this at least gives you some understanding as to how it might be, both in the finite and infinite case, you have an expanding universe that doesn't have a center at a particular place, and it doesn't have an edge, an outside. Well, the picture of the expanding universe introduced into astronomy and your thinking about the universe, the idea of evolution, change, and time. Because in an expanding universe, the conditions within the universe, the density of material, the temperature, these are continuously changing. And so different physical processes become possible at different times. And hence there is an evolutionary development of structure and types of structure. So here's a picture. We'll see this type of picture several times in the talk. Here is some measure of size. This is the separation between 2 points that we pick on in the universe. And here is time in billions of years. So our series picks the handy reference of 10 billion years. The best estimate for the expansion age of the universe is about 13.9, 13.8 billion years. I'll call it 14 billion years. This is an interesting time. It's quite sobering to think that if you walk around in the right part of the world, up in the north of Scandinavia, maybe even the north of Scotland, you can pick up a stone that's over 3 billion years old, just lying around on the surface. So if you just multiply that time by a factor of 4 or 5, you are going back to a time where there might not be any time. That there are all around us objects and structures that are not very far removed from what we think to be the apparent beginning of the entire universe. Well, this trajectory in green here is that of an expanding universe. If we locate ourselves here, 14 billion years, and run the clock backwards, let's go back to when it was contracted by a factor of 1,000. The temperature is 1,000 times greater than it is today. Today, on average, it's only about 3 degrees above absolute zero, minus 270 centigrade. So if we go back to this period where it is 1,000 times more contracted, the temperature is 1,000 times greater, more than 3,000 degrees. And there will be no molecules. There will be no genes. There will be no planets. There will be no stars. There will be no structures. There will just be protons, electrons, photons, other elementary particles. So the world is much, much simpler long ago than it is today. It is in thermal equilibrium, largely. And in thermal equilibrium, all you need to know is the temperature and the identities of the particles that are present. If you run the clock forward from that time when the universe is about 250,000 years old, it's 1,000 times contracted, what happens? Well, first of all, it cools off enough that atoms can form, then simple molecules. And then there are parts of the expanding universe which are going a little bit slower than the average because they've got more material in them. There's more gravitational pull. They attract more material to them. And eventually they separate off from the expansion, turn around, contract, condense, form large clusters of galaxies, and within them, galaxies and stars and ultimately planets will form. by processes that we don't fully understand. Increasingly, we can simulate those processes with fast computers to really quite high precision. But those problems are difficult in the same way that predicting the weather is difficult. I think not because we are missing some great physical principle, but because so many things are in play at the same time. It's hugely complex, and small uncertainties amplify chaotically to produce larger ones. So there's not going to be a sort of pencil and paper back of the envelope explanation for the complexities of star formation. Too many things are occurring. So as we run the clock forward, the first stars form, and then planetary systems, and then you'll hear later in the series about exotic processes that lead to simple and more complicated life forms. The whole picture is one that ends rather badly, we'll see. That we live in an interval of cosmic history after the stars have formed, but before all the stars exhaust their fuel and die. And the long-range forecast is rather bleak. The sun will eventually exhaust its hydrogen. It will undergo an energy crisis, expand dramatically, vaporizing the inner planets, and then eventually imploding to form a white dwarf star. We see that process occurring in other solar systems in our galaxy and perhaps further afield. And eventually all stars will cool and die, and the universe will become a great cemetery, a sort of cosmic cemetery of dead worlds. But in between, there is an interval of cosmic history, a habitable zone in time, and we live within that habitable zone. So I want in the next few slides to ask some questions which link up to that fact that we exist in this period. So, as several people have stated, and the theme of the series emphasizes, the universe is extremely old, more than 10 billion years in age. So should we be surprised by that? Why is the universe so old? And has it got anything to do with our existence? Well, in a very simple way, it does. We are all made out of elements which are heavier than helium. So these are what astronomers perversely lump together and call heavy elements. Anything that's heavier than helium. And 75% of the universe is hydrogen and nearly 25% is helium. And everything else is just a tiny trace element of a few parts in 100,000. But where do those heavy elements that make you and me come from? They don't appear ready-made at the beginning of the universe. They're made in the stars, in the final stages of the lifetime of dying stars. And in those death throes of stars, fast nuclear reactions take place, burning helium-4 and helium-4 into beryllium-8. And then beryllium captures another helium to make carbon, an interaction that's only possible, as Hoyle first noticed, because of a remarkable coincidence between the energy levels available in carbon nuclei and the combined energy of these two components. And then carbon can combine with another helium to make oxygen. Unfortunately, oxygen doesn't quite have a resonant energy level in the right place, or all the carbon would disappear and turn into oxygen. So these reactions are responsible for carbon and the successors, all the other heavy elements like silicon. But they take a very long time to go to completion, 1 billion or more years to make the basic building blocks of biochemistry. So we shouldn't be so surprised to find ourselves in a universe that's many, many billions of years old. Universes that were significantly younger could not contain the building blocks of biochemical complexity. There could not be DNA and all those other remarkable things that we just heard about. And we can go on from that to ask, should we be surprised that the universe is so big? Well, because it's expanding, the huge size of the universe is just a reflection of its huge age. So it's 10 billion light years in extent because it's 10 billion years old. So we could not actually exist in a universe that was significantly smaller than the one we find ourselves in. If the universe was just the size of the Milky Way galaxy, there would be 100 billion stars, maybe more planets than that number. This seems like a good economy-size setup to evolve complexity and life. But a universe the size of the Milky Way galaxy, with its 100 billion stars, would be little more than a month old. So there's barely enough time to pay off your credit card bill, let alone evolve complexity and life. So we should not be any more surprised by the huge size of the universe than we should be surprised by the existence of life itself. Often the huge size is used as an argument for making it likely that we find large numbers of outposts of life in the universe. We might well do, but the universe would have to be pretty much as big as it is just for one lonely outpost of life. Well, the size has another interesting consequence. The universe is actually almost empty. So to a first approximation, the universe is empty. It contains just about nothing. So if you were to smooth all the material, all the atoms in the universe, all the elementary particles into a continuous, uniform network, there would be on average just one proton, one atom, in every cubic meter of space. So no laboratory on Earth could make a vacuum that is as empty as that. So to a first approximation, the universe is empty. And again, this is a reflection of this enormous age and enormous expansion that it's undergone. The density has been steadily diluted for those 10 billion years of expansion. And today, the density is correspondingly extremely low. If you look at this picture in the background here, this is the famous Hubble Deep Field. So every speck of light you can see in this picture is a galaxy containing about 100 billion stars. And the whole global image corresponds to what you would see if you just held your fingernail up to the universe at arm's length. So that's how large the piece of the sky is. And if you look at the galaxies, you can see they come in all shapes and colors and sizes. So the bluey ones are rather young galaxies very far away, and the reddy ones are older galaxies that are closer to us. Picture was taken by just pointing the Hubble Space Telescope at a nice clear part of the sky with no local stars for a month, and just seeing what it found. Well, the most interesting part of this picture, though, in some ways, is not the blobs of light and galaxies. It's the dark spaces in between. We can pose a question, why is the universe, or the sky, dark at night? It was a question that was first posed by Edmund Halley over 300 years ago. Well, to be able to answer it, we need to understand this vastness of the universe just a little bit better. I said the average density corresponds to about one atom a cubic meter. If you gather those atoms into planets, it corresponds to running into a planet like the Earth every 10 light years, or a star like the Sun every 1,000 light years, or a galaxy like the Milky Way every 10 million light years. So you begin to see why the universe is not swarming with other civilizations and planets close by. The huge distance between stars and other potential forms of life in the universe is another reflection of the very low density of matter, and therefore of the very large age and very large size. Another consequence of that is that the universe is cool, as I was always telling our children, and we'll soon tell our grandchildren. And this is another reflection of the enormous amount of expansion. The temperature falls inversely as the expansion size scale. And so today the temperature is just a few degrees above absolute zero. Well, this enables us to say something about why the sky is dark at night. It seems a really strange question to ask. So when Halley posed the question first, why is the sky dark at night? People probably thought, you need to get out more, talk to people, do things. But his way of thinking was, well, if you look in the forest, out into the trees, in every direction, your line of sight ends on the trunk of a tree. And as you scan across the picture, you see just a continuous phalanx of tree trunks. So he asked, well, there are not many trees in this forest, but some people are trying to tell me that there are an infinite number of stars in the universe. But wouldn't that mean if I looked out into the universe, in every direction, my line of sight would end on the surface of a star? And so the whole sky should look like the surface of a star all the time. And there would never be any night. The sun would be completely overshadowed by the shining stars filling the whole sky. So this paradox was never answered until the expansion of the universe was discovered. The answer I've, in a sense, told you already, that there was a time when the sky was bright like that, but it was when the universe was 1,000 times more contracted and 1,000,000 years old, and the temperature was 3,000 degrees. So then the whole sky looked like the surface of a star, but there could be no astronomers in that environment. Today, the enormous amount of expansion has so reduced the density and temperature of matter that there's just not enough energy density around to illuminate the sky. If I clicked my fingers and turned all the matter in the universe into radiation using E equals mc squared, thanks to Einstein, all that would happen is that the temperature of the universe would go up from 3 degrees above absolute zero to about 15 degrees above absolute zero. And you wouldn't notice. So you see, there's just not enough energy in the universe to make the sky bright. So we've seen a sort of curious, almost philosophical set of consequences here, that if you want a universe to have the sort of broad brush ingredients that you need to make biochemical complexity, just to have carbon, oxygen, everything heavier, then such a universe has got to be big, it's got to be old, it's got to be dark, it's got to be cold, and it's got to be almost empty. Almost the exact opposite of the properties that all those philosophers of progress and people like Bertrand Russell tried to persuade everyone of in the early years of the 20th century and before. So these paradoxical properties, which sound as though they're not conducive to the evolution of complexity in life at all, turn out to be necessary properties in order just to create the building blocks for any type of evolution to act upon. Well, universes are like your stocks and shares. They don't always go up, they can also go down. And in fact, they can plummet. And here's our picture again of size against time. And the two types of universe that you can have are those we've seen already that run away and they keep on expanding forever. In fact, they're infinite in extent, in size. But there can also be universes which start to expand more slowly and don't have enough expansion energy to keep going forever. Eventually, they reverse and collapse back to a big crunch. In a sense, they start expanding with less than the escape velocity for the material contents of the universe, whereas these have greater than the escape velocity. In between, there is a single dividing line, a sort of British compromise universe, that I call it, that just manages to expand forever. I always tell a story about that. Many years ago, I had to go and give an invited talk about cosmology to Mrs. Thatcher, and which is a sort of eccentric thing that she would do by way of entertainment. And so I had to go and sort of do a 5-minute rehearsal for her very nervous advisors, worried that something might go horribly wrong and they'd be executed. And they asked me to talk for 5 minutes so they could judge whether this would be all right. And so I did, and I can remember must have shown something similar to this picture, and I made this remark about the British compromise universe in between. And afterwards, the special advisor said, he said, I thought that went well. He said, but I've just got one piece of advice. He said, when you come to give the talk to the Prime Minister, when you mention that British universe, try to be much more upbeat about it. It's just the sort of thing the Prime Minister likes to hear about. So it was good to know the country was in such sound hands. Well, one of the things that cosmologists do is to keep trying to reconstruct the past, moving further and further backwards in time to see if we can predict, using our mathematical model of the universe, whether there should be any fossils and relics that we can go and look for today, and therefore test the theory. So the curious thing about the universe is that when you observe it, you are always observing the past, because light takes a very long time to reach us. We don't actually know if the distant galaxies in that last picture are still there. They may have ceased to exist. We are seeing them as they were 10 billion years ago. But there are two great successes, our mention of this reconstruction. The first was predicted in 1948, although not noticed terribly in an era when the steady-state theory was very popular in Europe. So Gamow and his two students, Alpha and Herman, were interested in this idea of looking at the past of a universe that will be hotter and denser and more like a great experiment in high-energy physics. And they realized that you ought to expect heat radiation to be left over from that hot early beginning. And Alpha and Herman predicted that we should find today radiation background, black body radiation, with a temperature of about 5 degrees above absolute zero. And they published a relatively unnoticed paper in Nature predicting this. Later on, in 1964-65, this radiation was discovered by accident at Holmdel, New Jersey, by Penzias and Wilson, who subsequently received the Nobel Prize for their discovery. They worked for Bell Laboratories, the Bell Telephone Company's laboratories, and they had in their possession, as it were, the most accurate radio receiver in the world. And they were calibrating it in order to track the Echo communication satellite for the phone company. And they kept receiving in their detector this noise from every direction in the sky, and it was the same to high precision. And it didn't vary with the time of day, it didn't vary when the football team ran past, it didn't vary when the students were having their big party. So there was something that told you it was originating from far outside of the Earth. And eventually, they published their discovery, just a single measurement of frequency and an intensity. And their neighbors down the road at Princeton seized upon this. They had been planning to build a receiver to look for this radiation. Unfortunately, oblivious that all this had been predicted and essentially discovered theoretically by Alpha and Herman long before. And they wrote a companion interpretation paper announcing that Penzias and Wilson had discovered the relic radiation from the beginning of the universe. I always think this is very impressive. I mean, in Britain, we are pleased if the telephone company manages to connect our calls successfully 50% of the time. and wire up our computer connections so they occasionally work. But in America, the telephone company discovers the origin of the universe. Today, thanks to satellite observations, we've mapped this radiation over its whole frequency range, and it's a perfect Planck backbody spectrum, the most perfect heat radiation spectrum ever observed in nature. So on this picture, these circles are not data points and error bars. The error bars on this data are 10,000 times thinner than the thinnest line that would be visible on the picture. So it really is a perfect black body to an accuracy of a few parts in 100,000. So this radiation tells you that the universe was once hot enough and dense enough to produce a thermal equilibrium. This is the echo of the Big Bang. If you have an old-fashioned television set, we've got one, but it's in that repository of junk that Sydney, it's somewhere in a back room. You won't have any of these televisions. You'll be connected to cable and so on. But if you have an old-fashioned television, when you turn it on rather randomly, you get sort of white snow all over the screen if you detune it. A tiny percent of that snow, about 1%, is this microwave background radiation from the beginning of the universe. So by having a fancy modern television, you lose the opportunity to observe the radiation from the beginning of the universe. Too bad. This radiation starts to fly freely towards us when the universe was about 1 million years old. So that's that time I picked out when it's 1,000 times more contracted. So the density becomes low enough that the photons here don't interact with electrons anymore, they just fly towards us. And so when we detect this radiation, we're seeing a snapshot of the universe when it was 1 million years old. But we can do better. So if we keep going backwards in time to when the universe is just a few seconds old, it will be millions of degrees in temperature. So this sounds bizarre. How can you be talking about what's going on in the universe when it's 1 second old? But in fact, the physical conditions are rather modest. Because the density is so low today, 1 atom in a cubic meter, if you compress by a factor of 1 billion, 1 second or so, the density is only about that of water, 1 gram per cc. So there's nothing bizarre about that. We understand all the physics of this environment. But the temperature is high enough for nuclear reactions to occur. And protons and neutrons will combine to make deuterium, simple isotope of hydrogen, and then you can go on and make helium-3, so 2 protons in the nucleus, 1 neutron, and then helium-4, 2 protons, 2 neutrons. That's rather tightly bound. And it's hard for anything to form beyond that. There's no stable nucleus with mass number 5 as well. But this is a picture of what unfolds in time from 1 second, 10 seconds, 100 seconds, as the temperature falls from 10 billion, 1 billion, 10 to the 8 degrees. And you see that there is a build-up of helium-4 as deuterium, first of all, builds up, some destruction. Deuterium plus deuterium makes helium-4. But very quickly, it's all over. So the expansion cools the universe off, so the reactions just turn off. And you're left with these final abundances, about 24% by mass of helium-4, about 2 parts in 100,000 as deuterium, about the same in helium-3, and a few parts in 10 billion of lithium-7. The thicknesses are the ranges of the observations. Remarkably, these are pretty much exactly the observations that we see today, the abundances we see today, of all these elements everywhere we look in our galaxy and beyond. And ones like deuterium can't be made anywhere else. So the very lightest elements are believed to be made in the first 3 minutes of the universe's evolution. And these predictions allow you to test what you're talking about in cosmology right back to about a second after the apparent beginning of the universe. Well, up to about 1980, this type of scenario was reasonably well established. You had a very good description of the universe, but there were some puzzles in that the description had certain features that seemed very peculiar, that deserved explanation. And we might call these models the habitable universes that we just looked at. They've got to be expanding close to that critical sort of British compromise universe, what cosmologists call the critical universe. If you run away too fast, no stars and galaxies can cluster together and form. If you go too slow, you collapse before they can form. So you need to be quite close to that critical divide to be a long-lived, stable universe. But what's odd is that unless you start exactly on that critical divide, you always deviate further and further from it in one direction or another. And to be as close as we see the universe to be today, needed the starting speed to be tuned to an accuracy of 1 part in 10 followed by 35 zeros. So this seems bizarre. You know, how on earth could this situation have existed? The other thing about the expansion is it goes at the same rate in every direction. We say it's isotropic. Again, this seems very unlikely. Most solutions of Einstein's equations are not like this. And the ones that start like this gradually get further and further away from being isotropic. The other strange thing is that the universe is sort of slightly grainy, slightly lumpy, has stars and galaxies in it at a level of 1 part in 100,000. So it's not outrageously irregular, but it's not perfectly smooth. So we'd like to know, why does it have that exact level of irregularity? If the irregularity was 10 times weaker, there wouldn't be any stars and galaxies. There wouldn't be any carbon, there wouldn't be any us. If it was 10 times greater, 10 to the 4, everything would have turned into black holes long ago. And again, there wouldn't be any habitable regions. So this number is rather critical for us. And we'd like to understand why it's 10 to the 5 and not something else. Well, in 1981, Alan Guth introduced a new picture in cosmology, which is still the standard scenario. And this is now very long-lived. So a theory 1981 up to the present, this is the standard model in some sense. And it can have very complicated features, but I'll try to explain it in the simplest possible way. Here's our picture again of size against time. And you noticed, I hope, that when I drew this picture before, the trajectory of the expanding universe was always curving over in that sort of concave fashion as you went to the right. So what that curvature is telling you is the expansion is always decelerating. So once it starts expanding, gravity of the constituents decelerates the expansion. That's the explanation. The idea of inflation is that at some very, very early time, maybe as early as 10 to the minus 35 of a second, something happened and the expansion turned to acceleration. There was very good reason to propose this in 1981. Particle physicists were developing new theories that contained new types of matter field that possessed negative pressure and negative gravitating effect. So in effect, they were anti-gravitational in their action upon one another. We've discovered one of these types of particle now, the Higgs boson, a great fanfare a few years ago. So the idea was that these particles would be around, and then suddenly they would become more and more persistent, and then they would dominate the expansion and cause it anti-gravitationally to accelerate. But then they would decay into other ordinary particles and photons, and their normal service would be resumed. And this period of inflation turned out to have lots of dramatic effects. You can see on this picture, one of the effects is that it makes the universe much more expanded, much bigger than it would have been if it had followed that trajectory along there. So suddenly, up here, it's much more expanded than it would have been. And that drives the expansion towards that critical divide dramatically quickly. It ends up so close to the divide that even after 10 billion years of further expansion, you shouldn't be able to detect any divergence from the perfect critical expansion rate. The other thing it does is that no matter how complicated and chaotic and turbulent the expansion is here, once it starts to accelerate, all those deviations from smoothness and isotropy all just driven away. And at the end of this period, the expansion is perfectly isotropic in every direction to very high precision. So lots of our little puzzles all seem to get answered by this one simple idea. If we look at the same idea in another picture, you can see the last aspect of it. So here's our visible universe today. So that's as far as you can see with a perfect telescope. 14 billion years of expansion, 14 billion light years, that corresponds to this number of centimeters. And what we're interested in is how small can be the region which is going to expand to encompass the whole of our visible universe today. Without inflation, you need a region that's sort of that size, actual size, near the beginning of the universe, about a centimeter. That sounds rather small, but it's ridiculously large, because at the time of inflation, 10 to the minus 35 a centimeter, light signals could not pass across a region that was so large. So there would be no explanation as to why the region was so similar from place to place, direction to direction. What inflation does is that it enables you to grow the whole of the visible universe from a region that is vastly smaller, 10 to the 25 times smaller, so small that light signals can easily smooth out this region and keep it coordinated in temperature and density, so that after inflation finishes, the whole of our visible universe today inherits the properties and the conditions in that tiny, causally connected patch. There's a line of Shakespeare, I remember, that sort of summarizes this whole scenario rather beautifully. In Troilus and Cressade, he talks of the baby figure of the giant mass of things to come at large. So this is the baby figure of the giant mass of things to come at large. So the whole signature, the whole pattern of the structure of the visible part of our universe is inherited by the fast initial expansion and then slower later expansion of this tiny primordial fluctuation. Very soon, lots of people in the subject realized that you could exploit this in a remarkably different and powerful way. That little patch that's going to expand to become our whole visible universe will not be perfectly smooth. There must be some quantum fluctuations within it. The uncertainty principle alone prevents it from being perfectly smooth. And we could calculate what their signature, their spectrum should be, and then as they're inflated and expanded, they will show up in variations in temperature and density in the later universe. And they could be the fluctuations that ultimately turn into galaxies. And their intensity, which one might hope to compute, could give you the 10 to the minus 5 number that you need to explain the graininess of the universe. So suddenly you have a way of explaining that property and feature of the universe that doesn't depend on how the universe began, or even if it did begin. It's imprinted at a finite time soon after the expansion starts. Well, over many years, a sequence of astronomical satellite missions by NASA and ESA have been searching for those characteristic fluctuations in the temperature of the radiation which are predicted to exist. Here's a typical sky map. where the blue regions are showing you where the temperature is lower than the average, and the red where it is above average. Each change of color is a few parts in 100,000th of a degree. And if you take that whole sky map and average it across the sky, you can work out a sort of mean, here's the mean square, temperature variation from the average in microkelvin against angular scale on the sky. So the full moon is about here in angular size, half a degree. And the predictions of the simplest model of this sort are shown by the solid green lines. And we're going here to smaller and smaller patches of the sky. What the satellite does is to measure the temperature in that direction, then it measures the temperature, say, 1 degree away, and then it measures all 1 degree separation temperature distances over the whole sky, takes the average, plots it on this graph there. So what you see here is a rather remarkable agreement between the basic pattern of the observations and the theoretical predictions. The thickness of the blue is the uncertainty. It becomes very large here because there are not many independent 90-degree separation regions that you can fit in the sky. So there's a real limit on what statistical significance you can get on large angular scales. But on small scales, there's not really any limit. So this type of picture is enabling you to test directly a theory that you have about how the universe behaved when it was 10 to the minus 35 of a second old. And in these pictures is hidden all sorts of information. So remember the general shape. Here's just some examples. So if in your theory of the universe you change various other quantities you would like to know, like what's the fraction of material in the universe that's luminous, as opposed to some type of non-interacting elementary particle. And if you change that fraction here, going from sort of 2% to 6% and more, the message here is you see how the shape of that picture changes, how the peaks go up, the number of peaks changes. And in this picture, if you change the density of the dark matter, so the non-luminous fraction, again you see as you alter it from 0.1 up to a half or more, the overall shape of those predicted features changes. So the point to get is that hidden in those observations are very detailed pieces of information about things that you wouldn't have guessed it was telling you. How much matter there is in the universe, what's its identity, even how old is the universe, and so on. Well, that's the standard type of picture of inflation that most people take rather seriously because of this agreement with observation. But from it flows one or two other ideas that are rather extraordinary, that you take seriously just because of the success of the basic vanilla model. So very soon after it was proposed, people realized that this picture of having some tiny patch that accelerates, becomes large, becomes larger than our whole visible universe here, large enough and old enough so stars and galaxies can form, is only part of the whole story, because there's a lot more universe beyond that patch. Other little patches which could inflate in different ways for different periods of time. And so you should think of the universe rather like a great foam of bubbles. Some of the bubbles inflate a lot, some not very much, some maybe not at all. And we live in one of those that's inflated enough for there to be enough time for stars and carbon and planets to form. If we could look beyond our visible horizon, it's about 42 billion light years away, we would predict that eventually we should find the universe to be very, very different. We would see the expanded images of other bubbles that might have had very different conditions within them. So a prediction of this theory is that locally the universe is very smooth and isotropic, almost uniform with small fluctuations. But globally, it's highly inhomogeneous and completely different, potentially, to the world that we can see through our telescopes. There's always been a skeptical philosophical tradition that's overly positivistic and said, well, you cannot be sure that the universe beyond our horizon is pretty much the same as the universe inside our horizon. You must use the Copernican principle. You mustn't assume that things will be different for other observers in the universe and that we are special in some way. But this is the first time there's been a positive prediction that we should expect the universe to be very, very different globally to what it is locally. So one message here is the universe, the geography of the universe is a lot more complicated than geography used to be when you were at school. Worse than that, it turns out that history is more complicated than when you were at school. Because if we pick on this little patch that we just focused on, it turns out that this patch, any patch of this sort pretty much, has a rather awkward property. It has a feature that leads to producing further copies, further inflationary copies of itself. So once it starts to inflate, sub-regions within that inflated universe will themselves undergo further inflation. And they will then undergo further inflation. So it's like an unstable, self-reproducing process. And theoretically, it's predicted to have no end. We don't know whether it need have a beginning or not. So this is sometimes called eternal inflation or self-reproducing inflation. And it changes our picture of cosmic history because we have to regard ourselves as being in one of these inflated regions. But we now see that in a cosmic context, we're just one of these inflating regions. We've been produced by a tiny quantum fluctuation in the past. We don't know what the origin of that is, and we don't know whether we might produce further inflating regions in the future. So a question like, did the universe have a beginning, now has a much more nuanced answer. Our visible universe had a beginning. Its expansion began in a sort of quantum fluctuation. But whether the entire multiverse, as it's become known as, of all these regions had a beginning, we don't know. And maybe we can never know. So this type of picture is why suddenly there began lots of discussion in popular press, scientific press, about other universes and the multiverse. There are other places where you can generate candidates for other universes. But this picture is rather like a highly inhomogeneous and non-uniform universe, where in each place you visit, you will find conditions are very different. So it's like another universe compared to the region that we see and call our visible universe. Well, finally, I want to talk a little just about the future of the universe. Will the universe expand forever? So the universe is big, it's getting bigger, is it always going to keep on getting bigger? Well, in a way, the question is a rather moot one. Other unfortunate events will overtake us before we learn the consequences of whether the universe keeps expanding or not. So the life cycle of the sun, we are about 4.6 billion years from the apparent beginning of the sun and the solar system. There's a process of very slow warming of the sun that's got nothing to do with global warming, just as the sun is gradually exhausting its hydrogen. And then in another 5.5 billion years or so, there will be an explosive so-called red giant phase, where the sun expands massively and then implodes to form a white dwarf. So if our descendants are still around on planet Earth, they're going to have a difficult environmental crisis to deal with. Well, they probably need to be somewhere else. Here is a picture, care of the Hubble Space Telescope, of this cataclysmic process here that's sometimes called planetary nebula. It's nothing to do with planets and really nothing to do with nebulae either. It's just that long, long ago these objects on astronomical photographs looked like nebulae. And so this is a planetary system that's undergoing this implosion. There's perhaps two stars in it, or there's a magnetic field, because we've got two explosive rings. But the long-range forecast for the universe is rather more unusual. In 1999, we discovered by observing the expansion of the universe out to unprecedented distances because of the invention of a new way to reliably work out the distances to things at the edge of the observable universe, particular sorts of supernovae. And what was discovered was rather a shock, that when you looked out far enough, the universe's expansion was starting to accelerate. So the velocity against distance curve was starting to curve upwards. And here's our trajectory of size against time. What this was telling us was 4 or 5 billion years ago, the universal expansion started to accelerate. It's as though inflation were happening again. And it might be a similar type of energy field, might be doing this process in a different way in the late stages of the universe. There are now three completely independent ways of detecting this acceleration. It's evident in those microwave background fluctuations, it's evident in the Hubble expansion, and it's evident in what are called baryon acoustic fluctuations. So we feel that there's very good evidence that the universe is indeed accelerating, but why should it have started accelerating at this strange time a few billion years ago? Nobody really has any good explanation for that. It could be a random thing. There are scenarios where this does occur at random, but you would like to try and find a scenario where there is a definite prediction of the time when this should happen. The agent responsible has to be something which is anti-gravitating, okay? And it's been given the name dark energy to distinguish it from dark matter, which is just stuff that doesn't shine in the dark. So dark energy is not dark matter. Dark matter does not anti-gravitate. It gravitates. So if we look at the energy budget for the whole universe as we understand it, all our astronomical observations, 68, 69% of the total energy budget in the universe today is this anti-gravitating dark energy. So that's what's required to explain the acceleration. Of the rest, just under 5% is like the stuff that makes you and me, ordinary atoms. And the rest is so-called dark matter, and what distinguishes dark matter is that it's not atoms. So it's not things that undergo electromagnetic interactions or nuclear reactions. Things like neutrinos, and most likely very heavy new types of neutrino that CERN hopes to discover in the next year or two. Supersymmetric neutrino-like particles. I won't go into why you believe that. But this discovery of the acceleration of the universe brings us to a rather dramatic conclusion about the future of the universe. The fact that the universe is accelerating means that one day that acceleration will form around us a surface in the universe through which we can't see anymore. It's as though we are inside a black hole. The acceleration moves material away so rapidly that the light cannot overtake it and get to us. So we will discover at some time, or our descendants will, about 100 billion years in the future, that they can't see anymore any distant galaxies. All those galaxies in our astronomical pictures will have passed out through that horizon surface. All the stars, all the other galaxies will have passed out. We will not be able to see any other galaxy. So astronomers at that epoch, if they just appeared with no knowledge of the past, would know nothing about other galaxies. They wouldn't be able to make any observations to determine the expansion of the universe or the fact that it was accelerating. Worse still, that background radiation that we talked about, they wouldn't be able to see that either. Because rather earlier, when the universe is 70 billion years old, that background radiation so falls in wavelengths that its frequency becomes equal to the plasma frequency of our galaxy and the interstellar medium within it. And those photons cannot penetrate our galaxy anymore. And we can't make observations of that black body radiation that Penzias and Wilson discovered. So that whole realm of cosmology is ended. And the things like helium and deuterium that told us so much about the past, their abundances would gradually and slowly be distorted by the outproducts of all the stars that have evolved over hundreds of billions of years. And their abundances will have deviated greatly from the primordial predictions. So what we see is a curious feature of the evolution of the universe. We've seen that there is a period where evolution and persistence of life is astronomically possible. There are the building blocks of life, and they're around for some time before all the stars die. But there's also a period that's propitious for the understanding of the universe. That we live in an epoch of cosmic history when we can observe all these external galaxies, when we can deduce that the universe is expanding, that it had this exotic history, and that something like inflation occurred in the far, far distant past. Any astronomers that exist in the far, far future, 100 billion years after the beginning, will not be able to make those observations. They won't be able to determine that we sit in a universe of galaxies and black body radiation with this exotic history. The only way they'll be able to do that sort of cosmology is by reading old books. Cosmology will be a type of literary history. You could read old volumes of the Astrophysical Journal back in the era when people could see far, far distant stars and galaxies. So this is a strange and sombering thought that Sidney stressed. Things don't necessarily always work for some overwhelmingly good-seeming purpose, that there are unexpected aspects of the universe and unexpected future aspects of a type of universe that's really quite conducive to the persistence and evolution of biological life in the present epoch. Thank you.